Hi everyone. In this video we're going to be talking about the concepts of continuity and discontinuity, and we'll be using limits to kind of explain those. The good news is we've already done a lot of the legwork in pre-calc, but I do have a few new things to teach you. The first thing I want to talk about is a type of discontinuity that we haven't really discussed before, and that's called oscillating discontinuity. A classic example would be something like the function sine of 1 over x. And let's talk about what that looks like. So if I pull up my grapher here, let's turn that off first. So let's just look at the inside, because we said the function was sine of 1 over x. So let's talk about what 1 over x is doing as x approaches 0. So see how 1 over x approaches positive infinity on the right side, approaches negative infinity on the left side. But these y values grow faster and faster. Well, if we start taking the sine of those y values, check out what happens to our graph. See how it's almost like it's oscillating back and forth between +1, -1, +1, -1, +1, -1, +1, -1. And it keeps going faster and faster. And I'm doing my best to zoom in with my fingers here, but as you can see, it's going to start bugging out my computer just because there's so much graph there. It's hard for me to pinch zoom without, actually touching the graph. But even if we do it, yeah, in fact, it's actually slowing down my computer as it's recording. So what do we talk about, or how do we describe that limit? Well, basically, we're actually just going to say that function does not have a limit as x approaches 0. We'd say that limit doesn't exist. Some of the other discontinuities we've talked about were infinite discontinuities. This is synonymous with vertical asymptote. Obviously, it doesn't have to look like the example I gave you. We could also see a vertical asymptote where, like the function we were just looking at, 1 over x, where we've got it approaching positive and negative infinity on different sides. Let's see. We've also talked about jump discontinuities in pre-calc. That's where the function just abruptly jumps from one y value to another. Typically, the y value is actually defined on one side, like see how I filled in the circle here, but it doesn't have to be. You can have a jump discontinuity where you have two open circles as well. Let's see. With limit statements, what defines a jump discontinuity is when the limit as x approaches some number, let's just call it a, from the left side of the given function does not equal what the function is approaching from the other side. So see how I've got my right side notation over here, I got my left side notation there. When these two don't equal each other, that is what defines a jump discontinuity. And then finally, we have removable discontinuities. That's synonymous. You called them holes in previous classes. And that's where the function actually does approach some value from both sides, but the function might not necessarily exist there. See, I've left an open circle. It could exist at a different y value. For example, this would also be a removable discontinuity, something like this, and then we've got a y value for that point. Both of these are considered removable discontinuities. But again, the big thing on this one is that the limit from both sides equal each other. Another way you could say, whoops, I said a approaches as x approaches a from the right side equal to. You could also simplify this by saying just the two-side limit exists. Limit as x approaches a of f of x exists. Because remember, we said the two-side limit only exists if the two one-side limits equal each other. Do I need to say anything else? Yeah, we would just say, but that limit does not equal the actual function value. That's all that matters. As for the infinite discontinuity, we didn't really leave any function notation there, but basically you'd have them approaching either positive or negative infinity. It could be the same, it could be opposites, it doesn't matter. Okay, so let's turn the page. Got a couple examples here. Our task is going to be to identify where the discontinuities are and classify what type of discontinuities they are. So we've got, looks like 3 examples here, and I'll just start working the first one. Up here we've got a function y equals x minus 2 over x squared minus 4. And just think about what we would have done in pre-calc. We probably would have stopped and factored that, which we then would have simplified. So I see it looks like these will divide out. And from here, we would have come to the conclusion that because we divided out the x minus 2 term, that's what made it a removable discontinuity. Removable discontinuity at x equals 2. And then because we had a non-removable one left behind at at the x plus 2 term, so that x equals -2, we'd assume, or in previous class, we would have called that vertical asymptote. We can also call that an infinite discontinuity. Infinite discontinuity at x equals -2. Remember why I made such a big deal last semester about you not saying, oh yeah, there's a hole at, and let's see, in this particular example, it'd be 2 comma 1/4. And I said, well, it's because the function doesn't actually exist there, so you can't really call it a point. The way we're going to describe it is using this new limit notation we've been talking about. So we could say the removable discontinuity is at x equals 2. The limit of the function as x approaches 2 is 1/4. That is the correct way to do it. Again, we don't want to be saying there's a hole here because that's just informal. All right, moving on. Our next one is kind of an interesting graph. You see the absolute value, and you see the same thing in the denominator. We had an example or two like this, I think, all the way back in the limits investigation. So if you've forgotten kind of what that looks like, well, one way you could think about it is if you just plug in a few values. So plug in a few values. What you're going to see is you basically wind up with either y equals 1 or y equals -1, depending on what you picked for your x values. Hopefully you're asking yourself, okay, what happens if I plug in x equals 2 or something around there? Well, that's kind of the dividing point, right? Because we have x minus 2 in both of these. That would actually be where our jump discontinuity occurs. If we were graphing this, so there's my 1, there's my -1. Let's see, we'd have 1, 2. We'd have negative values for the function up until x equals 2. And then it would switch to positive values after x equals 2. But if you actually plug in 2, you're not going to get anything because you divide by 0. So we would call this a jump discontinuity. And again, we know because the limit on the left side is not the same thing as the limit on the right side. 2 from the negative side, f of x. And we can just simplify it by saying it does not equal the limit as x approaches the same number just from the opposite side. Finally, our last one's a fifth root function. We haven't worked a lot with fifth roots, maybe not at all. The good news is all the odd roots kind of look similar. Obviously, the curvature changes a little bit, but since we haven't talked about that one that much, let's just pull it up here. Turn the old one off, and there it is. So let me zoom out a little here. So see how it kind of looks like the cube root function? I mean, obviously it's not. Obviously it's a little different. It just, the curving happens a lot faster here than it does in the cube root function. But otherwise, we can take the fifth root of a negative number. We can take the fifth root of a positive number. So it looks like there's actually no discontinuities here. Well, any real x value, I guess. So, question here, before you flip the page, we do have a question. can a limit exist at a point where the function is discontinuous? I'll let you think about it for 3, 2, 1. And the answer is yes, it can. In fact, that was our definition of removable discontinuities. Okay, so our next problem deals with the definition of continuity, which we kind of teased a few pages back. Where was it? I think it was in 2.1c. Yes, on page 17. So if you want to flip all the way back in your notebook, at the bottom, or we talked about continuity in the middle example, and I think we defined continuity. Again, this is back on page 17. We're going to use that definition more today. So what I'd like for you to do is pause the video and just try and fill these out, maybe in pencil or something. Well, hopefully in pencil. It's math class, right? And I'll come back in a few seconds and give you the answers. Okay, welcome back. Here's what we got. First off, does the function at 1 exist? Yes, you can see it down here with the red point. I filled it in red, make it easier to see. Does the limit as x approaches 1 of the function exist? Yes, because both on the left and the right side it's approaching y value 1, which I highlighted in green. Do the previous two answers equal each other? Unfortunately not. And therefore, by our definition of continuity, the function is discontinuous at that point. And again, that's because the limit as x approaches 1 was not the same thing as the function's value there. The final question was, where is the function continuous? Unfortunately, I don't really have a quicker way for you to write this other than using interval notation. So sorry for making it so messy. I won't give you one with 3, 4, 5 pieces too often. I'm not going to say never, but not too often. Let's see, bottom of the page, essential question. What must be true for a function to be continuous at a point? That is our old definition. Whoops, I meant to underline, I scratched it out. And we just wrote it up here. Well, we wrote the discontinuity thing up there, but it'd be the limit as x approaches some number of a function has to actually equal the function's output at that number for a function to be continuous. Let's turn the page. All right, first off, I've got a piecewise function here, and then we've got a zillion different limits to answer about it. So let's give you a second to graph the piecewise function. Then we'll start talking about the limits. All right, so hopefully your piecewise function looks a little bit like this. I tried to color code it for you so you could really see what was going on. Pay close attention to the endpoints. Really want to point out to you that in both of them, on the left side, it's just a less than. It does not include the equals to. So notice how I've marked that with a pair of open circles here. Okay, so now we've got all our definitions. There's a laundry list of limits here for you. Let's pause the video and try and fill in the limits. Okay, so there you go. The task was a little bit similar. In fact, it was very similar to ones we've had before. But what may have gotten you, or at least may have confused you a little bit, were these limits that I marked with arrows here, where it kind of referenced something that didn't happen. So for example, the very first one says, what's the function doing as x approaches 0 from the left side? Well, we aren't told. We weren't given anything that defines the function from the left side. So that limit simply cannot exist. And then as for C, this one you may have gotten wrong, however you thought about letter A. Remember, the definition of the regular limit, just as x approaches the number, said the limit from both sides has to equal the same thing. So I'm worried I'm not doing a good job of explaining that. So basically, because the limit as x approaches 0 from the negative side does not equal the limit as x approaches 0 from the positive side, you cannot say the limit as x approaches 0 exists. Oh, I should have put the f in there. Hopefully that makes my answer for C make more sense. Because this one didn't exist, well, it really didn't matter what happened over here. No matter what, because they weren't the same thing, we were going to arrive at this conclusion. Let's get the rest for you here. I don't know if you need a little more time to look at it. As for the rest, I think this kind of matches up with what we talked about before. The last thing we need to do is talk about which one or which type of discontinuity occurs where. And if we look at x equals 3, see how we have the abrupt jump in values. So we have a jump discontinuity at x is 3. And then looking at 0, well, we do have that open circle, right? Let's go ahead and call that a removable discontinuity. At that endpoint there. Here's a good one for you. What must be true for a function to be continuous at an endpoint? So, see like how right over here on the right side, the function's coming up, it approaches it, and it actually occupies that value. The function is continuous there, right? Like, it's not broken in any way, other than the fact that I guess we just didn't really talk about what happens to the right of x equals 5. So we are going to update our definition of continuity a little bit. It's going to be a special case where we're looking at an endpoint. In that case, we'll say the one-sided limit. One-sided limit. If that equals the function, then the function is continuous at that endpoint. So I'll just write it out fully in limit notation. If you'd like that translation, then we'll hurry up and finish because I know this one's getting long. So there you go. I'll let you pause the video if you need that, and then we'll turn the page. Okay, so we've got another piecewise function here. Again, let's take a second to graph that real quick. This time it's two linear functions. Okay, there we go. First off, our job is to figure out where are any points of discontinuity. I find a point of discontinuity at x equals 2. And then part B says describe. Is it removable? Is it non-removable? Let's see. Well, removable was basically a hole. And this looks like a jump, so this is actually going to be a non-removable. And that's because it's a jump discontinuity. If you want to leave yourself a little more explanation on how you knew it was a jump discontinuity, it's because the two one-sided limits did not equal each other. All right, for our last one, it's no different in that we're still given a piecewise function, but maybe it's one that'd be a little more annoying to graph, or we just don't want to take the time to graph it. So I'll show you how to evaluate just totally by hand. Task is still determine whether, or I guess slightly different task, but same idea. Determine if the function is continuous at x equals 2. We're given a piecewise function. Basically, the point where you're checking is always going to be, or almost always going to be the point that is the break or the transition point in the piecewise function. But you're still going to basically have to run the check. Does the two-sided limit exist, and does it equal the function there? So basically this is what we're checking. Limit as x approaches 2 from the left equals the limit as x approaches 2 from the right, and that has to equal f of 2 for continuity. If any of these, basically if either of these two equal signs turns out to be a does not equal, or like any of these two, if any one of these things does not equal the other two, then the function is not continuous at x equals 2. So let's check them real quick. Let's start with the limit as x approaches 2 from the left. Well, from the left side, we're working with the cosine function. See how it's x is less than 2? So that's what's happening on the left side. That would be limit as x approaches 2 from the left side of cosine of pi over 6 times x, which the cosine function is continuous everywhere, so you can just substitute in 2 right away. That would be the cosine of pi over 6 times 2, same thing as the cosine of pi over 3, which, think about your unit circle, tick, 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 that is 1/2. All right, now let's check the second one. The limit as x approaches 2 from the positive side. Limit as x approaches 2 from the positive side. Now on the positive side, we're working with this other one here, so x over 4. Limit x approaches 2 from the positive side of x over 4, which would just be 2 over 4, which reduces to 1/2. Happy day. And finally, we need to evaluate f of 2. So let's check, okay, this one, the bottom one, is the one with the equal sign. So again, we'll evaluate just 2 over 4. Hey, that reduces to 1/2. Nice, because all three of these equal 2, or all three of these equal 1/2, the function is continuous at x equals 2. So honestly, the way I'd write it out will be just like this in my answer. I'd say the limit as x approaches 2 from the left side equals the limit as x approaches 2 from the right side equals a function which equals 2. Therefore, therefore, f of x is continuous at x equals 2. Thanks for hanging in there. I knew this video is going to be long, but it's a lot of similar things all bleeding together. Have a good night.